Electrical circuits can often feel overwhelming at first because you're handed a pile of equations but no clear strategy for how and when to use them. In this lecture, I will show you an exact method for finding the current, power, and work done for any DC circuit. By the end, you will know about Kirchhoff's laws and understand how to use them effectively. In the last lecture, we discussed how to calculate the power and work done in a basic series DC circuit. In Lecture 6, we introduced the concepts of electrical currents and resistance. And in Lecture 5, we introduced the battery, which holds a roughly fixed potential difference across our circuit. With this knowledge, we now actually have all the tools we need to calculate the useful properties of any DC circuit. However, we haven't really come up with a foolproof strategy to do this. And not just for a series circuit like this one, but also parallel circuits, where the current can flow along multiple paths. Here is a simple example of a parallel circuit with 3 paths and 3 resistors. Now, as we've discussed previously, the battery voltage is known, and it almost entirely depends on what's going on inside the battery rather than the circuit itself. As we said in Lecture 7, there is an internal resistance, which will slightly affect the voltage supplied to the circuit, but for simplicity, we'll assume that this is approximately 0. We usually know the resistances beforehand too. These can be figured out by knowing what our resistors are made of and their dimensions. Resistance does also depend on the temperature, but we'll just assume that it stays roughly fixed here. All in all, the values for the battery voltage and the resistances are more or less fixed no matter the circuit design. What we don't know, however, is the size of the current and the power outputs. Our goal is to come up with a system for finding these for any circuit design. In 1845, German physicist Gustav Robert Kirchhoff proposed 2 very simple laws for electrical circuits. The first of these, known as Kirchhoff's current law, states that the electric current into a point is equal to the electric current out of it. Obviously, this is true for a point on our wire, but this law is most useful in parallel circuits where the current can take multiple paths. The current into this junction must be equal to the current out of it. In other words, if we label the current along the path going into the junction as I1, and the current along the 2 paths out of it as I2 and I3, I1 equals I2 plus I3. This is completely logical, because the current is just charge flowing, and we cannot create or destroy charge. So the charge going into a point must equal the charge coming out of it. To be clear though, this does mean that the measured current can be different at different points in our circuit. In our parallel circuit of 3 resistors, we have 4 junctions in total. We can label the current for each path, and in this case, we get 7 different currents in total, which I've labeled from I1 to I7. Using Kirchhoff's current law, we can write out equations for all of our junctions. We get I1 equals I2 plus I3, I2 equals I4 plus I5, I6 equals I4 plus I5, and I7 equals I3 plus I6. You'll immediately notice that our third equation is equivalent to the second, so we can say automatically that I6 equals I2. Our last equation is also therefore just I7 equals I3 plus I2, meaning I7 is equivalent to I1. So we can remove these 2 latter equations. If you look at our circuit, these results should be of no surprise to you, as our circuit is symmetrical. Now, one thing I should say when labeling currents is that the direction isn't always obvious. In this system, it's easy to see which way the current flows, but if there was a path like so, it's not obvious which way the current will go. This is not a problem, however. Just make a guess of the current direction, and if you're wrong, you'll just get a negative value for the current later on. Just make sure to apply the law to each and every junction in your circuit. We'll need all of these expressions in a moment. All in all, Kirchhoff's current law should seem completely intuitive to you. Kirchhoff's second law states that the potential difference or voltage provided by a battery or batteries must be equal to the voltage drops caused by the resistors or other electrical components over any closed loop in the circuit. In other words, no matter what path our current takes, the voltage gained and lost must sum to 0. The potential drop throughout the loop must be equal to the potential gain from the battery. So in this example, the potential drop must be 3 volts, no matter which way the current flows. Once again, this is completely intuitive. In our parallel circuit, there are several paths that the electric current can go to get from the positive terminal of the battery to the negative. Let's go through each one and apply Kirchhoff's voltage law. The first path is highlighted like so. Along this path, the current simply flows through the first resistor with a current I3. As we know from Ohm's law, the potential drop when moving through each resistor is I times R. So we can say for this loop that the voltage provided by the battery, V battery, is equal to I3 times R1. It's as simple as that. We can also do this for the second path, where V battery equals I5 times R2, and for the final path, where V battery equals I4 times R3. Applying Kirchhoff's laws to our circuit, we now have everything we need to find the current values throughout. From the first law, we found that I1 equals I2 plus I3, and I2 equals I4 plus I5. From the second law, we found that V battery equals I3 times R1, V battery equals I5 times R2, and V battery equals I4 times R3. Our next task is to crunch the numbers and figure out what each current variable is. Feel free to pause the video and see if you can find the current values yourself before I continue. Firstly, we can easily find I3, I5, and I4 by simply rearranging our expressions from the voltage law and substituting in our values for V and the resistances. Doing this for our first equation, we obtain I3 equals 0.6 amps. For the second equation, we obtain I5 equals 1 amp, and lastly, I4 equals 3 amps. We can then use these results to find the other current values. Using our second equation, I2 equals I4 plus I5, we get I2 equals 3 plus 1 equals 4 amps. Using our first equation, we get I1 equals 4 plus 0.6, which equals 4.6 amps. And just like that, we now know the current everywhere in our circuit. Let's return to our circuit diagram and write out our values for the current. Using this, we can find the power output through each resistor. If you recall, the power expended by a resistor is the current through each resistor squared times the resistance. So through R1, the power is I3 squared times R1. Through R2, it's I5 squared times R2, and through R3, it is I4 squared times R3. We can use our values for the current to calculate these. A good way of testing whether you're on the right track is to find the power provided by the battery. This is simply V times the current through the battery, which in this case is I1. If we do this, we find that the total power provided is 13.8 watts. As we know, energy cannot be created or destroyed, so the power in must equal the power out. The power out of our circuit is simply the sum of the power expended by each resistor, which we find equals the power in. If the total power in does not equal the total power out, you've gone wrong somewhere, as you are breaking the laws of physics. If we want, we can also easily calculate the work done by each component over a period of time delta t by simply multiplying the power variables times delta t. So overall, using Kirchhoff's laws, we can find the current, power, and work done for any DC circuit. These two laws are extremely powerful and apply to any DC circuit no matter how complex it is. Let's quickly summarize our strategy. Step 1. Guess the current directions and label the regions in the circuit with different currents. Step 2. Apply Kirchhoff's current law to every junction in the circuit. Step 3. Apply Kirchhoff's voltage law to every closed loop in the circuit. Step 4. Solve the system of equations to find the current everywhere in our circuit. Step 5. Use the current values and resistances to obtain the power dissipated through each resistor, and multiply by delta t to obtain the work done over a period of time. Now, truth be told, the parallel circuit we solved was a very easy example. Most circuits are a lot more complicated than this, and using this method, you can end up with a lot of equations, which can be pretty brutal to solve. However, it turns out that there are two very neat shortcuts we can take when dealing with lots of resistors. Firstly, let's consider a series circuit made up of 3 resistors. If we apply Kirchhoff's current law to any point in our circuit, the current in must equal the current out, and as there's only one path, the current must be the same everywhere. This should seem obvious. Now if we apply Kirchhoff's second law, the voltage is equal to I times R1 plus I times R2 plus I times R3. If we factorise this, it's just the current times the sum of the resistors. Therefore, we can say that this circuit is equivalent to a circuit with just one big resistor, which has the resistance of the three resistors added together. In other words, in a series circuit, the resistances are summed, and we can simplify a circuit like so. You can apply this to any situation in a circuit where there are resistors in series, no matter how many there are. The second shortcut we can make applies to parallel circuits. If we consider two resistors in parallel and apply Kirchhoff's current law, I1 equals I2 plus I3. Applying the voltage law, the first path yields V equals I1 R1, and the second path yields V equals I2 R2. Rearranged, we get I1 equals V over R1, and I2 equals V over R2. Summing these, we get I1 plus I2 equals V over R1 plus V over R2. From the current law, I equals I1 plus I2, so I equals V times 1 over R1 plus 1 over R2 in brackets. Rearranging, we get V equals I times 1 divided by 1 over R1 plus 1 over R2. We can therefore replace the parallel resistors with a resistor R with a resistance equal to 1 divided by 1 over R1 plus 1 over R2. A neater way of writing this is that 1 divided by R equals 1 over R1 plus 1 over R2. This is the second shortcut, and it can be applied to any parallel junction in a circuit. In other words, 1 divided by the resulting resistance R is equal to 1 over R1 plus 1 over R2, and so on for all the paths in parallel. Overall, these two rules can be very useful for dealing with complex circuits with many series and parallel paths. Let's quickly run through this example. We can start by simplifying the series resistors, so we can let R8 equals R1 plus R2, R9 equals R3 plus R4, and let R10 equals R6 plus R7. We can then simplify these three resistors we see in parallel, letting R11 equals 1 divided by 1 over R9 plus 1 over R5 plus 1 over R10. Finally, we are left with two resistors in series, so we get one resistor equal to R8 plus R11. We can say that V equals I times this resistor, and if we expand this in terms of our original resistances, R1 to R7, we get the following expression. This can be very useful, as we can now quickly find the total current through our circuit and the total power output. Let's now summarise the contents of this lecture. Kirchhoff's current law states that the current into a junction equals the current out of it. Kirchhoff's voltage law states that the sum of the voltage provided and the voltage expended along a closed loop must be equal to 0. For any DC circuit consisting of a battery with a known voltage V and resistors with known resistances R, we can use the following step-by-step method to find the current and power expended. We can make shortcuts for systems of resistors. For resistors in series, we can just add the resistances together, and for resistors in parallel, we can say that 1 over R equals the sum of 1 over the resistors in parallel. So, we can now deal with series and parallel circuits made up of resistors and batteries. As we said, every conducting material has a resistance, besides some extremely special ones called superconductors. In general, resistance is simply the scattering of electrons while they move through a medium. However, resistance is actually only the first of three fundamental features of any electrical conductor. The other two are known as capacitance and inductance. Now we've mastered basic resistor circuits, it's time to make things more interesting. There are many other electrical components out there, and they all manipulate the flow of charge in unique ways. In the next lecture, we're going to talk about a device known as the capacitor. We introduced capacitors much earlier in the series when talking about fields and potential, but adding capacitors into circuits can lead to lots of interesting new physics. In the next lecture, we'll discuss the physics behind capacitors, how they control the current, and the clever devices they can be used to make.